Okay. So today uh, I would like to define another subgroup out of any subgroup in a group. So suppose we consider a group G and H be a subgroup of G. Okay, H be a subgroup of G. Fine. Now let us define a subset of G with respect to a given element small g belongs to capital G. Okay. So suppose you consider one element from the group, and then with respect to this element, you are going to define one subset of that group by. So what is the definition? What the notation is like that: G H G inverse. The notation is like that: G H G inverse, but it defines a set consisting of the elements of the form G X G inverse, where X belongs to capital H. Okay. So this notation defines a set consisting of the elements like this form Gx G inverse, where X belongs to H. Okay. Now note that E belongs to GH G inverse. Why? As E can be written as G E G inverse, where being a subgroup, E must be in H, right? So therefore the identity is in GH G inverse. So having sitting inside the set GH G inverse, we are tempted to check whether this subset of G will form a subgroup of G, as because the identity is sitting inside that subgroup. For that reason, we are always going to check whether it is a subgroup or not. Okay. So to prove that, for proving this set is a subgroup, let us consider two elements. Say Gx G inverse or Gx1 G inverse, and another one you may take Gx2 G inverse belongs to Gh G inverse. Okay. Then first compose these two elements. So Gx1 G inverse composed with Gx2 G inverse. Now then, using associativity, you can write it as Gx1 G inverse G, x2 G inverse. So that means now this G inverse G being the inverse of G, so G inverse G is identity. So Gx1 E x2 G inverse. So then it is G x1 x2 G inverse. Now since H is a subgroup and x1 and x2 both are in, you may write it down as like that, x1 x2 belongs to H. So x1 x2 belongs to H means their composition is also in H. That means x1 x2, the product x1 x2 is also in H. So therefore it is in GH G inverse. Okay. Also, if you take anyone, suppose gx1 G inverse, and what would be the inverse of this element? This is inverse of G inverse, x1 inverse and G inverse, right? That means, so inverse of G inverse is G and it is x1 inverse and it is G inverse. Now since x1 belongs to H and H is a subgroup of G, so its inverse is also in H. So that means it belongs to GH G inverse, as x1 inverse belongs to H, right? So this proves that GH G inverse forms a subgroup of G or any small g belongs to capital G, right? So taking any element from the group, you can associate a subgroup of G out of any subgroup of G, right? So suppose you have a subgroup H, and then for any element G, GH inverse will going to be a subgroup of G, right? So these subgroups are called conjugate subgroups of a subgroup H of the group G. Okay, conjugate subgroups, right? This one, conjugate subgroup. Okay, note that note that note that one can associate a map from H into GH inverse by. So if is from H goes to GH, G inverse defined as f of H equals to GH G inverse for all H belongs to capital H, right? So if you have any subgroup, then for any G, for any element G of the group, you can associate one conjugate subgroup, and then from the given subgroup H into the conjugate subgroup GH inverse corresponding to the element G, you can associate a map, right? And this map, interestingly, this map F is both 1 1 and on 2. Why? Why it is 1 1? Because just take GH1 G inverse, GH2 G inverse. Suppose the images are same, and from this one by cancellation law, so left cancellation you can cancel out this G, by right cancellation you can cancel out this G inverse, and you are going to have H1 equal to H2 by using cancellation laws, right? Right? And this proves that F is 1 1. Why it is on 2? Why it is on 2? Because for any y belongs to GH G inverse. Okay. Okay. Then G inverse YG, it belongs to uh, yeah. Mm, so G inverse. Okay. Yeah. Sorry. So y belongs to this. Yes. Then there exists x belongs to h, such that y can be written as gx t inverse. That means, so this x is in h. So gx g inverse is actually fx. So that means corresponding to any y belongs to gh g inverse, you can definitely have one x belongs to h whose image is y. So that means the map is onto. Okay. So this proves that any subgroup of a group G is equipotent with its conjugate subgroups. Okay. So the number of, that means that is cardinality of H is equal to cardinality of GH G inverse for any G. Okay. Right. So their conjugate subgroups will have the same elements as that of the given subgroup H. So that is an interesting feature. Okay. Fine. Okay. Now, so yeah. Now let us move to the discussion of cyclic subgroups, cyclic groups, and we are going to investigate that how their subgroups do they look like, right? The subgroups of a cyclic group. So that is an interesting feature. Already you have seen that in the group of integers z plus, the precise complete list of subgroups are nz, right? Where n greater or equal to 0. Nz. So these nz's, so yeah. So observe that this nz is generated by n. That is, nz is actually the cyclic subgroup generated by n, L angle R angle n, right? In Z plus. So this emerged. So from this one, so one concept is emerging out that subgroups of a cyclic groups may be cyclic because of this example. But before going to state this, you need to prove that every subgroup of a cyclic group must be cyclic. Then you can say that yes. So because it is a subgroup of that cyclic group Z plus, so it must be cyclic and it must be generated by some n. Okay. Although we have not yet used this fact while proving this, that these are the subgroups of Z plus. We have used only the division algorithm of Z plus, right? Now the proof of characterization of subgroups of Z plus involves the fact that two things. The one important thing was that well ordering principle, and the second one was division algorithm, right? Now, interestingly, if you look at this statement, okay, so let us write down the theorem that every subgroup of a cyclic group must be cyclic, right? Now, while proving this theorem, we will see that the proof was exactly the way we have proved the subgroups of Z plus R precisely in Z. Because in this proof, we also used the two facts. One is well ordering principle and another one is division algorithm, in the same way as we have done for this one. Okay, this one. So let us have a look at this one, at this proof. Okay. So what to do? The first move will be to consider one subgroup. So let H be a subgroup, any subgroup of a cyclic group G, which is generated by. So since it is a cyclic group, so it must have a generator. So it is generated by some small a. Okay, that is G can be written as L angle R angle A. Okay. So the elements will be a to the power n, n belongs to Z. Okay. So these are the elements of the cyclic group G generated by small a. Now we need to check that H is also a cyclic group generated by some element of H. Okay. That we need to check. Now first of all, if H is the trivial group, then we are done. We have nothing to prove, right? So we have nothing to prove for this case because it consists of only one element, singleton identity. So we are done. If not, if not, if not, if it is not the trivial group, then there exists some non-identity element x belongs to H, right? So H must contain some non-identity element x. But being a subgroup of G, this x is itself in the group, in the whole group. So this x, so being an element of G, there must exist some n belongs to Z such that x can be written as a to the power n, right? So x looks like a to the power n or some n as it is in the whole group G. Okay. Now this n, so since x is non-identity, so this n will not be 0. So it is either less than 0 or greater than 0. Now if it is greater than 0, then we do not go further. But if it is less than 0, then so if n greater than 0, then we do not proceed. If not, then now since n is less than 0, if not means n is less than 0. So then a to the power minus n, what does it mean? I have already proved that it is a to the power n inverse, right? So that means being, so a to the power n belongs to H, x is a, so this belongs to H. So its inverse is also in H, being a subgroup of G. So this is again in H. Now see that this minus n is greater than 0. So without loss of generality, you may, without loss of generality, you may, one may say that there exists a positive n belongs to Z such that a to the power n must be in H. Okay. So you must have some positive integer n for which a to the power n must be in H, capital H, right? Now you set, now we set capital P. It consists of all those n belongs to Z plus, for which a to the power n belongs to H. Okay. And since a to the power n, okay, just take it m, yeah. So since a to the power n belongs to H, where m greater than 0, so this set is non-empty, as a to the power m belongs to H, where m greater than 0. Okay. So P is a non-empty subset of P is a non-empty subset of Z plus, and hence by using well ordering principle, there exists n naught, there exists n naught belongs to Z plus, which is the least element of P. That is, n naught is the least positive integer for which a to the power n naught belongs to H. Okay, n naught is the least positive integer for which a to the power n naught belongs to H. And this process up to now, it coincides with the scheme of the proof while you are proving the subgroups of Z plus R in Z. So that is the same. So we are just copying the proof in this version. If you look at the proof earlier in the case of Z plus, you will see that the proof is exactly the same way we are doing here. Okay, so a to the power n naught belongs to H. Now, so our claim is that this H will be generated by, now our claim is that, what is our claim? Claim is that the H is the cyclic subgroup of G generated by e to the power n naught. So this is our claim. Okay. Now note that since a to the power n naught belongs to H, note that since a to the power n naught belongs to H, so taking any power of n naught, it must be in H, being a subgroup, right? Being a subgroup of G. So taking any power of a to the power n naught, you will see that this belongs to H. And this implies L angle R angle a to the power n naught is a subset of H. Okay. So it remains to check the reverse inequality, right? So for the reverse inequality, let us suppose that B belongs to H, be any element. Okay, and we would like to prove that this B is generated by a to the power n naught. Okay, so our goal is that there exists some K belongs to Z such that B can be written as a to the power n naught to the power K or a to the power n naught K. Okay, right? So this is our goal. Okay, so now to prove this, we need to call the division algorithm here, as we have done in the proof of Z plus. Okay, so now we would like to use division algorithm. In the division of division algorithm. Okay, now since B belongs to H, so B is in H, and H is a subset of the whole group G, and has been generated by A. That means B. So there exists some M belongs to Z, such that B can be written as A to the power M. Okay, but we will prove that B will take the form A to the power N not K by using division algorithm. Okay, so now by using division algorithm, in the division of M by N naught, there exists K R belongs to Z, such that M can be written as N naught K plus R, where 0 less or equal to R less than N naught. Okay. Okay. Now, if R is strictly greater than 0, then if R is strictly greater than 0, then M minus N naught K equals to R implies A to the power R equals to A to the power M minus N naught K. Okay. That means, so you can write it as A to the power M dot A to the power minus N naught K. That means A to the power M dot A to the power N naught K inverse. Now see, A to the power M belongs to H because B is A to the power M, and A to the power N naught K is also in H, as because we have seen that this is a subset of H. So any power of A to the power N naught is in H, and so is their inverse. So this inverse is also in H. So this is in H, this is also in H. So then you take the compose, and H being a subgroup of G, so this composition is in H. So this implies this A to the power R belongs to H, where 0 less than R less than N naught, which says that R is a positive integer less than N naught, for which A to the power R belongs to H, but it violates the property of N naught of being the least positive integer for which A to the power N naught is H. N naught belongs to H. So that means this leads to a contradiction. So whatever we have assumed was wrong. So R is equal to 0, which implies that B equal to A to the power M equal to A to the power N naught K. That means A to the power N naught to the power K. And hence H is a subset of L angle R angle A to the power N naught. Okay. That is H equals this cyclic subgroup generated by A to the power N naught. This completes the proof. Okay. So this completes the proof. So you have seen that every subgroup of a cyclic group must be cyclic. Okay. Okay. Fine. Now also one remark should be made here. that every cyclic group is abelian, right? Every cyclic group is abelian because if you take as because if G be a cyclic group generated by small a belongs to G, then for any two elements uh, x y belongs to G. So x y equal to, now x can be generated by a to the power some n, so it is a to the power n dot, y can be generated by some a to the power n, and you take the composition, and then using in law of indices it is a to the power n plus m. Then this n plus m and m plus n both are same because z plus is abelian, right? So therefore it is a to the power m, a to the power n again, and it is yx. So hence every cyclic group is abelian. But the question is that does the converse hold? Hold in general, right? Support your answer. It is your task to provide one example which does not satisfy this, the converse part of above result. That is, every cyclic group is abelian. So the converse will be every abelian group is cyclic or not. But you can find out it is not, that the statement is not true in general. You can find out one abelian group which is not cyclic at all. But you need to find out which is the group you can have amongst the groups that we have already talked about. Okay, fine. Okay. Now, okay. Now, okay, I would like to give you an exercise that suppose we consider Z plus. Okay, then yeah, then for any two integers, then for any two integers, definitely need two positive integers. Yes, positive integers n comma m. Now, nz plus mz. What is that? This is actually this group that I have already discussed, HK. So if you remember the construction, it is HK means HK, right? Where H belongs to capital H, K belongs to capital K, right? So this, the composition here is the composition of the group. Now the composition for Z plus is plus. So that is why we are writing NZ plus NZ. Okay. Okay, but this group is actually, it is dz. What is d? Where d is the GCD of n comma n. Okay, and prove that if you take the intersection, because intersection of two subgroups is again a subgroup, so it is CZ, where C is the LCM. It is the LCM of n comma n. Okay, okay, just try this out now. This one, nz plus mz is actually dz. Just do it on your own now. Okay, করো, এটা করো, 5 মিনিট সময় নিচ্ছি, করো। dj nz plus mz is equal to dz. এটা দেখো তো কি করা যায়। nz plus mz is a subgroup of z plus. So being a subgroup of z plus, it is of the form some d naught z, right? Now you need to check that this d naught is actually the GCD of n comma n. So this is your task. Just do it now. Okay. Can you hear me now?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So first of all, nz plus mz is a subgroup of z plus, and for this reason, you will get some d belongs to z plus, such that nz plus mz equal to dz. So our claim is that d will be the GCD of n comma n, and for to check this, you first need to check that d is a common divisor of n and n. Okay. Now note that this n, so n is equal to n1, right? That means n1 plus m0. So it is in nz plus mz, but nz plus mz is dz, right? So n is in dz. That means n equals to some dq. N equals to some dq. Okay. So okay, so this implies d divides m. So in a similar way, you can say that d divides m. So in a similar way, you can say that d divides m. That means d is a, so d is a common divisor of n and n. Now it remains to check that d is the greatest common divisor of n and n. That means if you take any other common divisor of n and m, then suppose c is any other common divisor of n and m, then you must have to show that c divides d, right? Okay. So let c is a common divisor of n and m. That is there exists xy belongs to z such that n equal to cx, m equal to cy, right? Right? Okay. Now, since dz is equal to nz plus mz, so in a similar manner as we have seen in the case of n and m, that n and m are in dz, so in a similar way you can show that d is in nz plus mz. So d is actually d1. So d is actually d1. So it belongs to dz, and dz is our nz plus mz. This implies d can be written as n x dashed plus m y dashed, right? N x dash plus m y dashed. But here you have proved that n is actually cx, m is actually cy. So just put these facts here. So you will get cx x dashed, cy y dashed. That means c, so taking out all along, so c into x dash plus y dash, right? So that means where this x dash plus y dash is an integer. So this proves that d is a multiple of c. That means c divides d, and hence d becomes the GCD of n comma m. So thus, if you take any two positive integers n and m, then nz plus mz will be generated by the GCD of n and m, right? So that is nz plus mz is GCD of n comma m z. Okay, just this one. Now I am leaving the other fact that if you consider the intersection, then you will get that. So proof nz intersection mz is actually lz, or L is the LCM of n comma n. Okay, so that I am leaving up to you. Okay, fine. Okay, okay. Now, yeah, okay. Now let us move to the discussion on generating some new groups out of a group and a subgroup. Okay. So what is the way of thinking about these facts, these concepts? The way is that, so next discussion is like that. So let us consider a group G and a subgroup H, okay, of G. We define a relation on G with respect to H by the following. What is the relation? So suppose you take for A comma B belongs to G. Now we say that this A is equivalent to B modulo H. Okay, this is a notation actually. This is a notation of the relation that A is congruent to B mod H. If and only if, so when one does say this one, the condition is A is equivalent to B mod H if and only A inverse B belongs to H. Okay, if you see that two elements for two elements AB, if you see that A inverse B belongs to H, then you say that A is congruent to B mod H. Okay, this is a definition of the relation. Now, whenever you are defining a relation, a binary relation on a set, so you are going to prove, you are going to check that whether it is an equivalence relation, right, or whether it is a partial order relation, right, whether it is reflexive, symmetric, transitive, or whether it is reflexive, antisymmetric, and transitive. Right. So let us see that for any A belongs to G, for any A belongs to G, you see that A inverse A, right? Now, what is A inverse A? A inverse A is the identity, and being a subgroup of G, H contains the identity. So E belongs to H. So A inverse A belongs to H implies A is congruent to A modulo H, right? That means this relation is reflexive. So it is reflexive. Okay. Now for A comma B belongs to G, suppose that A is congruent to B mod H. That is, which implies that A inverse B belongs to H. And this implies just taking the inverse. So this belongs to H, being a subgroup. That means B inverse of A inverse belongs to H. So it is B inverse A belongs to H. And that means A B is congruent to A mod H. This holds. So it is symmetric. Also, let A B C belongs to G such that A is congruent to B mod H, B is congruent to C mod H. So, since A is congruent to B mod H, so A inverse B belongs to H. And since B is congruent to C mod H, so B inverse C belongs to H. And since these two elements are in H and H being a subgroup of G, so if you compose them, it will be again in H. So that is A inverse B dot B inverse C belongs to H. So taking so using associativity, so it is B inverse C belongs to H. That is A inverse E C belongs to H. That is A inverse C belongs to H. And this implies A is congruent to C mod H. So it is transitive, right? So hence, so this proves that the relation defines an equivalence relation on G with respect to H, right? So this relation defines an equivalence relation on G with respect to H. And while you are defining an equivalence relation, you are going to partition the set, right? With respect to equivalence classes, distinct equivalence classes. So we need to find out what are the equivalence classes this relation describes. Okay, so for any, suppose you take any A, then its equivalence class is so class of A. So it contains all those B belongs to G, such that which are congruent to A. Which are congruent to A mod H, right? So this class contains those elements which are congruent to A mod H. That means those B belongs to G, such that A inverse B belongs to H, right? Those B for which A inverse B belongs to H. That means those B, such that A inverse B will look like A inverse B equal to H for some small h belongs to capital H, right? That is, those B belongs to G which are taking the form of AH for some for some H belongs to capital H, right? So that means this shows that class A contains those elements which are actually taking the form of AH, A composed with H. What is H? H is in capital H. So just compose each element of capital H by A, you are having the whole class determined by A. So this is the class determined by A. So this class contains the elements which are, you can say that, multiples of A with respect to the composition of the group. Okay, and you denote this set like this one, A H, and we define this class of A as the left coset of H in G determined by A, right? So left coset of this is left coset of H in G determined by A. Okay. Okay. So this is the left coset of H in G determined by A. Okay. Note that. Note that. Note that. So we know that any two equivalence class with respect to an equivalence relation defined on a set is either disjoint or identical. So note that for any two AB belongs to G, so this A will determine one left coset of H in G and B will determine a left coset of H in G. So H, so either AH equals to BH or AH intersection BH equal to phi. Okay, right? Now it should be observed that so it should be observed that now AH equals to BH means, what does it mean? That is means the classes determined by A and B are same, right? Now you see that you have already studied the fact that two classes are same if and only if they are related. A is related to B, right? So that means, so here you can impose the same thing here, that AH equals to BH means the classes are same with respect to A and B, which implies that A and B are related. Now here relation means implies that A is congruent to B mod H. So A and B are related with respect to the relation defined above, right? That is, if and only if, so A congruent to B mod H means if and only if A inverse B belongs to H. Okay, so you can write that. So AH equals to BH if and only if A inverse B belongs to H, or A comma B belongs to G. Okay, so in this way you have this one, right? Also note that for any small h belongs to capital H, suppose you are considering the elements from the subgroup itself, then for any small h belongs to capital H, the left coset of H in G determined by small h, what is that? So this is actually H. Why? As because H inverse E. What is H inverse E? just putting H instead of A and E instead of B here. Just putting H instead of A and E instead of B. So H inverse is H inverse. Now since H is in the subgroup, so its inverse is also in the subgroup. So H inverse belongs to H, which implies H is congruent to E mod H. And since two elements are congruent to each other, so they are related to each other. That means their classes are same. Okay. So if you take any element from the subgroup, then its left coset coincides with the subgroup itself. So HH is capital H. Okay. Okay. So I think I should stop here for today.